Hi everyone, this is Gwen from Nile, and today I want to talk to you about PGVector. What is PGVector? PGVector is an extension to Postgres that allows you to store and search for vectors, usually nearest neighbor search or similarity search. And these vectors usually represent images or documents, so you are really looking for similar images or similar documents based on the distance between vectors that represent them. When do you want to do this kind of thing? There's a lot of use cases. So if you're using some kind of an AI chatbot and it's the kind that uses RAG, so it looks up documents and then feeds them to the LLM, and you need the documents to be relevant to your questions so the LLM can give a good answer. This is usually done through a vector store with vector similarity search, but there is a lot of others. Sometimes you just take a picture of a product and you want to find more products similar to it, or you're looking for a restaurant you're going to like and you want recommendations. And so vectors are used for a lot of those machine learning use cases, and not just the usual ChatGPT, although that obviously made vector stores a lot more popular. So Postgres, being the database for everything that it is, has PGVector as a vector extension, and I want to tell you a bit about it. So first I'm going to tell you why I think you're going to want to use PGVector. Then I'm going to show you how to use PGVector. So you'll see how to store some vectors, how to find them later, how does similarity work. And then I'm going to tell you how does PGVector work with Nile, because combining PGVector with Nile lets you do this kind of similarity search and build this kind of recommendation or chatbot system based on tenant data. So tenants can have their own private data, and the vector search will only find vectors within their private data store. So I'll show you how to do that. And then I'm going to show you some of my favorite PGVector features that not everyone knows about. So you'll get to hear about some of the more advanced functionality and consider yourself an expert. So first things first, why PGVector? So first of all, if you don't need vectors, you don't need PGVector. So let's assume you're going to need to store vectors. Most of the time, you're going to need to use them in some kind of a customer-facing application. If you look at all my example movie recommendations or searching for the documents you need in a Wikipedia kind of situation, or if it's finding relevant text to feed it so it can answer questions, they are use cases in the application itself, right? So you need some general data for your application, an image that represents the movie, and the title, and the director, and the list of the main actors, and maybe a synopsis. Like all this information you also have to store. It's not just the vector. And of course, there's just the general flow of your application. So you have user login, and you have the user profiles, and you have who else is in their family and likes watching movies. Dedicated vector store will usually mean that you're going to have one database for the rest of your application and one database for the vector store. Now this is doable, but kind of a pain, right? You have to manage two connection pools. A lot of things that the user wants to do in the UI, they end up calling two different databases. You have to reconcile the results in your app. You have to decide whether to show partial result or wait for the slower one to return. Like all this adds quite a bit of complexity. There is something really nice about doing the usual selects on one familiar database as we're used to, rather than adding all this complexity. All this would not be an enjoyable conversation if PGVector sucked. But in fact, it's a fairly reasonable, perfectly valid vector store. It does pretty well when compared to others. As a normal vector store, it does all the normal things. So you can obviously store vectors. It all allows you to store both dense vectors and sparse vectors. There's different algorithms that generate different types of vectors. It allows you to search for vectors. It supports exact search, also known as flat index. It allows you to do approximate search. It supports the extremely popular and extremely effective AgentsW. It's an approximate nearest neighbor, and in PGVector, it's implemented as an index. So it allows you to use the best, latest, and greatest algorithms to find vectors. It allows you to use all kinds of distance metrics. It supports 6 or 7 of them, which is kind of the standard. In addition to supporting full-sized vectors, it also supports quantization. So it only supports the relevant chunk of the vector, meaning that you use less memory and have much faster searches. And then, of course, it is Postgres. So you get all the cool stuff about Postgres. It works with literally every language in the world. It is ACID compliant. It supports SQL. You can do joins, so you can actually get a lot of relevant information to your vector in the same query as the vector, and you can slice and dice things in different ways. It has, point-in-time recovery. It supports pgadmin and all those tools. It supports pgdump, like all these things that you like and enjoy in Postgres work. And of course, 35 years of being stable in production is a pretty big deal. Most vector stores cannot really boast the same track record that you get just by using Postgres. So as you can see, I'm a huge fan of Postgres, and I really believe in Postgres all the things, and PGVector being one of them. I hope I sold you on how awesome PGVector is. You're now itching to give it a try. Let me show you how to try it. So obviously I'm going to show you everything on Nile. I logged into some existing database. You start, as always, by creating a table. And you have an embedded column, and you can see that the type is vector. This is what PGVector gives you, essentially, a vector type. You specify the size of the vector. And the size that you specify have to be exactly the size of the vectors you're planning to store. So usually you use some kind of an embedding model that returns a vector with a specific number of dimensions. This is the number you need to use. This number is never 3. The small ones may be 300. The large ones may be 3,000 or 30,000. Definitely not 3. But I'm doing a small example here, so I'm going to use small, highly visible vectors. I really like doing small examples for educational purposes. It is so easy to start with the gigantic 1500 dimension vector, and then you get some results and you cannot eyeball it. So you get some distance. And is it the right distance? Did I make a mistake? Are those neighbors really the nearest neighbor? If you have 3 vectors with 3 dimensions each, super easy. If you have 100,000 vectors with 1,000 dimensions each, you're going to have really hard time knowing if your query is doing what you think it's doing. We start small. One other thing to note here is that this is a tenant-aware table. What does it mean? It means that each vector belongs to one tenant. It looks like we're inserting everything into one big table. But behind the scenes, Nile distributes the data into what we call virtual tenant databases, essentially maybe a bit like partitions. Each one of those records belong to a virtual tenant database. So when I connect to a virtual tenant database and start running queries, I find vectors that belong to that tenant, and I will not find vectors that belong to different tenants, which is obviously great if you are into privacy and security. And let's start with inserting a vector. So, as I mentioned, small vectors are awesome for learning. This is the tenant ID, but the tenant ID has to belong to an existing tenant. So let me check if I actually have any tenant here, and I do. So let me copy the ID of the existing tenant. Okay, and we have inserted our first vector. Yay! Now, once we have vectors, we usually want to query them, and those are usually nearest neighbor queries. So Nearest neighbor, as you can imagine from the name, it's all about distance. There is all those different ways to measure how far vectors are from each other. As I said, PGVector supports many of them. It supports L2 distance, which is the Euclidean distance. So what I'm doing here is basically saying, show me the document and the distance to 312. Let's run that. And you can see the distance here. As I said, PGVector supports 6 different distance metrics. I'm not going to get into all the differences between all of them. The choice of the distance metric really depends on the algorithms that generated the vector. Usually the vendors that provided the algorithm will tell you which metrics are safe, and cosine distance is usually safe. So this is, you can see the operator, this is the L2 Euclidean distance, and then cosine distance, which, as we said, is the most popular distance metrics that most vector generation algorithm, the embedding algorithm, support. So we searched it, and as you saw, the search was kind of fast. And the reason it is kind of fast is that we only had one vector to search, and this vector is small. If you have 100,000 or 1 million vectors and they're each 1,000 dimensions, it's going to have to load a lot more of them to memory in order to scan 100,000 vectors. You have to load 100,000 vectors into memory. If they have 1,000 dimensions, they take about 3K each. It's a lot to read into memory, which is where vector indexes come in. Those are not your run-of-the-mill indexes. Vector indexes are essentially an implementation of approximate nearest neighbor algorithm in Postgres index form. And the idea is that instead of scanning all the vectors, it finds clever ways to divide all the vectors into neighborhoods, and then you place your input vector into the same grid. It finds the nearest neighborhoods, and then it searches for nearest vectors inside those neighborhoods. So it can miss some things in case a farther away neighborhood actually has one vector that is closer to us. So it's, again, approximate. This is in the name, but it's obviously a lot faster because you search just the places where this can include. So I just described IVFF flat. Agents W does something slightly different. It basically has layers. The top layer is very coarse grained separation of the vector space, and then it gets more and more fine grained as you go down the layers, and there is connectivity between all the vectors in each layer. So you basically use those connections to kind of drill your way down and find the most relevant vectors in all those layered map kind of situation. Generally speaking, IVFF flat indexes are much faster to create, but they have worse trade-off between performance and recall. So if you try to make the query faster, it will perform worse and you may miss some neighbors that you actually expected to find. AgenSW, with all the layers, it takes a lot of time, a lot of resources to create, but once it's created, 2 good things about it. Once, it keeps getting updated as you insert, and it does it well, so you don't have to rebuild, or not as often at least. And it has pretty good trade-off between, even when you tune it to be quite performant, it still mostly finds what you need. So you can usually when you look at vector benchmarks, you see a graph with what is the recall, what percent of the vectors we expected to find we actually found, versus throughput. And if in IVFF flat, you can kind of see it crash. As you need more accuracy, throughput tanks. In AgenSW, you see this nice smooth decline, so you can have more control over at what kind of recall you need and what is the performance you're going to get out of it. Creating an index works more or less like creating an index. You shouldn't be very surprised about it. One thing to notice, you have to specify which operation. So this is an index that will be used when we do the L2, Euclidean distance. If I'm going to do cosine distance, I'm going to need a different index. And I can create a bunch of those if I'm going to use different distance metrics, but honestly, don't. Those vectors take a lot of resources both to create and to store, and nobody ever needs two distance metrics. Both HNSW and IVFlat allow you to specify some parameters for the index. If you see here, we are creating HNSW again. It has two parameters, M and EF construction. M is the maximum number of connections. So remember, we have those layers. Each layer has some vectors, and they're all connected to each other. So you can use them to drill down and kind of explore the fewer connections means less to explore. Things will be faster, less recall. EF construction is how many candidate vectors you consider when building the index. If you consider more vectors, it takes longer to build, but obviously you get a better graph at the end that better represents your data. Okay, so we saw how to insert vectors, search for vectors, and create indexes so we can search faster. I want to show you what those kind of distance queries, when I talk about similarity search in real-world applications, they don't really look like the query I just showed you. If you look at the query here, it's basically show me the distance for all those documents, right? This is not how you usually use vectors. The way you normally use vectors would be a lot more like this. So I want a bunch of documents from wiki documents, and I want them to be similar to the document represented by this embed. I want them to be similar means that I want the distance to be fairly small. If something is very far away, not very similar, I'm going to filter it out. So this is this where condition. Now I want them ordered by similarity. If you think about, you Google, you don't even think about it. We're so used to it. If you Google, the documents on top are usually the more relevant. And then as you go down the list, those are less relevant documents. We want that in our result. So this is the query you usually run. And you can see that you get the tenant, you get the document ID, you get the embed. Now this will search all the documents. And I just told you that for privacy, it is really, really important to search the documents for a specific tenant. So we need to connect to a specific virtual tenant database, so we will not have to filter by tenant. If I have another tenant, I created another tenant, and I'm going to insert a vector for the other tenant. Let's make the vector. We'll make it the same vector, but we'll give it a different ID. Let's try both queries. We'll start with this normal, give me the 10 nearest neighbors. And you can see that I now see both tenants. If I do this first, this is the second tenant. You can see that because I selected the second tenant, I now see only result for the second tenant. Even though I don't have any where clause, this is exactly the same query from before. You can see that you can use similarity search with vector distances as normal, but you can also do it in a way that preserves tenant security and privacy. So we talked about PGVector, how to use it normally. We talked about how to use it with Nile. Let me tell you, and I'm not going to demo, I'm just going to talk you through it, some of the features that I think are really cool and not enough people actually know about them. So I already told you about HNSW. I cannot say it's obscure. A lot of people blogged about it, but I still hear people say that PGVector is slow, and then when you dig a bit, they say it's because it doesn't support HNSW. Well, it supported it for the last year, so get on with the program and use HNSW indexes. Other than that, PGVector supports quantization. This is newer than HNSW indexes. That was added back in April. And quantization basically means that, vectors have 1,000 numbers, more or less, and each one of those numbers is a floating point. Floating point that uses 32 bits to represent it. So 32 bit times 1,000, it's like 3K. Not all those bits are actually all that important. I mean, Some of them represent numbers that barely matter for distances. There are only for tiny differences. Those are the millimeters, right? If you have things that are kilometers from each other and then you have some things that are millimeters from each other, maybe you don't care that much if two documents are so similar that they're like millimeters away. This idea lets us basically say, okay, let's save the important half of the vector or the important quarter of a vector. So you basically cut everything by half, latency, every resource you can imagine. Try it out. In my experience, it's a trade-off that is very, very well worth it. So quantization. The other lesser known feature is actually very new, and it was shipped literally last week. So that new. Like we went from shipped last year, shipped in April, shipped last week, and I'm talking about iterative index scans. So one downside of the approximate vector indexes is that they didn't combine well with other indexes or other filters. So if you wanted to do something like find all the relevant documents in this tenant, but also filter them. I only want the documents that belong to this topic, only Chinese restaurant, please. I don't want German restaurants. Those filters would be applied after the similarity search finished running, meaning that you would first find the n nearest neighbors and then throw away everything that the filter leaves out. So you find 20 restaurants, maybe quarter of them is Chinese, you move them out, now you're left with 15. This means that you actually need to retrieve a lot more neighbors than you actually need, right? Because you will be tossing some of them out later and the customer still expects the top 10 results in the search, right? So what iterative index scans does is basically, as it sounds like, right? It iterates. So it scans the similarity search index, gets the nearest neighbors, filters out everything that you told it to filter out. Now it has a smaller set. Are those enough to return a response? If yes, fantastic, return a response. If not, scan some more, get us more similar vectors, filter some more out. Enough now. So you kind of rinse and repeat and keep on scanning and filtering until you have enough results that the query requested. The way to use it is that you take your index and you basically say, I want to enable iterative scan. For age NSW, there's two ways. One is that the ordering is exact. It reduces recall a bit, but you get good order. If you use relaxed order, then it may mess up the order between two close by vectors, but you will get a lot better recall. And of course, you can reorder or re-rank them later. So you don't actually have to worry about it too much. Relaxed order seems to be quite fantastic. And one last thing. As you may have noticed, I just showed you a bunch of essentially toy examples. Toys are fine. I like playing with toys. They're educational toys. I recommend playing with some educational toys, but eventually you will want to build a real application. PGVector is fantastic because it has integration with a variety of languages, and in each language it supports a lot of different clients and ORMs. So when you decide to write an application in Python or JavaScript or Go or whatever it is you like, go to the PGVector repository and look for the integration with this language and with your favorite client or ORM. Pretty much every example in this list under Nile template uses PGVector. And we use them in different languages. So we have one in Next.js, and we have one that uses Prisma. We have one that uses Python. We have an example that uses Python with Llama Index. So we have repositories for all of them. We explain how to build them and how to use them. You can take a look here and see that, hey, we're using SQL Alchemy and we use PGVector's SQL Alchemy integration. And then this allows us to define this column as a vector. So you can really see exactly how this is all done. Hopefully, I gave you all the reasons you need and all the tools you need to get started with PGVector. And if you're building a multi-tenant application, then you can see how to use it with PGVector and with Nile and get vectors, similarity search, and privacy. If you're building something cool with PGVector, I really encourage you to tell the world about it, whether or not you're building it with Nile. And the reason is that I keep getting into internet conversations where people tell me things like, nobody is using PGVector, or PGVector is slow using a 2-year-old benchmark. Like, I don't care if people make choices different than I would, but I feel like they have to be informed choices. And it seems like there is a lot of misinformation about PGVector, and people may be making suboptimal choices because they think nobody is using it, when I know for a fact this is not the case. And if you use it, then you know for a fact that this is not the case. So join the fight against misinformation online and tell the world about the awesome things you've been building with PGVector.